So the next thing we're going to be looking at is what happens when our vector sum does not end up being a right angle triangle. In that case, we have to look at some other methods for solving those. There'll be two major ways we can do that. One is using vector components, and one is using something called the sine and cosine law. We'll start with the vector components. Now this is the most general solution, and what this means is that this one's going to always work. So it doesn't matter how many vectors there are, how they're going to be oriented, you can always use vector components then to solve it. The reason why we sometimes don't use it, or often don't use it, is it's not always the most efficient way of solving it. So it works for everything, but it's not always the easiest way to go. So there's really three cases where we're going to have to look at. The first case we've already looked at. If you have three vectors that are arranged such that a right angle triangle is formed, if you're doing that, you really want to use Pythagoras' theorem, so c squared equals a squared plus b squared, or that SineCosine. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tan is opposite over adjacent. And that's going to be far and away the most efficient approach. So if you can use the right angle triangle, you should definitely do that rather than doing components because it's going to be much faster. The case where you have to use vector components is if you have more than three vectors. So if you have three vectors, you can make a triangle. If you have more than three vectors, you can't make a triangle. And so for more than three vectors, you can't do a triangle problem. The last case, and this is the one that's going to be most common in this section, is if you have three vectors that are arranged such that a non-right triangle is formed. So they will be similar triangles to the ones we've done before, except that there won't be a right angle in those. So here we have two options. One is you can use vector components, and so it's going to be a perfectly good way of doing those. You can also use something called the sine and cosine law. Now these are on your formula sheet, and we'll go through those in a few minutes here. We'll start with vector components though. And so when you're doing vector components, there's a couple steps that you need to do. What we're essentially going to do is just split up every vector into a horizontal and vertical component. Now when you're doing that, one of the things that's really, really important is set a positive and negative direction. Now you'll have to do that for both the horizontal component and the vertical component because again, we're doing them independent of each other. And you will have motion in both directions in both planes. So set a positive and negative direction for the horizontal plane and the vertical plane. It doesn't matter which vector or which direction you take is positive and negative, just as long as you're consistent all the way through the problem. You'll separate each vector into its horizontal and vertical components. Again, don't forget to include those negative signs for anything going in the negative direction. Then we're just going to add them together. Now, some of them, because they have negative signs, you'll end up subtracting them, but we can think of that as adding a negative. So to get the net horizontal, we're going to sum up all the x components, and the net vertical, sum up all the y components. Once you have that, now you have just a net in x and a net in y. Those two are always at a right angle to each other, so now it turns into just a right angle problem. So we can take the net horizontal and net vertical vectors, that's a right angle, and so the hypotenuse is going to be the vector sum. And then we can use sine, cosine, or tangent, then typically tangent, to solve for the angle. So let's do an example with the vector components. So for this one, we're going to be looking for the net displacement of an object that's traveling along four different segments. Now for this one here, because we have more than three, we can't use a triangle to solve this, so we are going to use vector components. Keep in mind, if you did want to try to do this geometrically, you'd have actually five different sides to your figure. You have four different vectors that you're adding together, and then you also have the net one on top of that. So you have a five-sided figure, which would be difficult to solve geometrically. So that's why we do these with components. So we're going to split everything up into x and y components, and we'd highly recommend just putting that into a table. It's just going to make it a little bit easier to keep track of everything and keep all of your values straight. So we have one column with the x component, one column with the y component, and then we'll just look at each individual vector then along those two components. We should also, of course, always have a positive and a negative sign. So I'm going to take east to be my positive direction for the y component, and then I'll take north to be the positive direction for my y component. Now again, you could flip those and make west and say south your positive ones, doesn't really matter, but just make sure you pick one and are consistent all the way through. Now our first vector then is the 120 meters north, and so that one's just heading straight 120 meters to the north. And so we can see that there is no x component, there's no east-west motion in there, so I can just put 0 meters in for there. And then my y component is the full amount there. Now north is my positive direction, this is in the north, and so this is then a positive 120 meters. My next vector is going to be due west, and so this one's just heading in this direction, 70 meters. So it's at 70 meters west. So this one here, I see that I have all that in the x component and then none in the y component because there's no north-south movement if I'm going west. Now I've taken east to be my positive, and so I do need to write this one in as negative 70 meters. And so do make sure that you are watching your directions when you're doing each of your vectors. The last two we are going to have to split up into vector components using sines and cosines. So the first one, 25 meters east, 40 south. And so I would recommend doing is just drawing a coordinate axis here and then drawing your angle relative to there. This is that shorthand notation for the cardinal reference system. So we start on the east axis, which is our reference axis, and go 40 degrees to the south. And so that's going to be drawn down here. And then the 40 degrees is going to be then to this east axis here. So we are going to have two components to this. We're going to have then, of course, the x component, and then we'll have the y component overall. So if we look at these, and you don't have to actually do the trig ratio each time, but what we can do then is if we just look at the horizontal component here, that's going to be cosine. So I can take cosine of 40, and that's going to be then the x component all over top of the hypotenuse, which is 25. Which is just the length of the vector or the hypotenuse of this one here. Now when we solve this, I'm just going to multiply this to the other side to be the x component. So what I generally recommend is you can, if you know that, just jump straight to there. And so I'm going to have 25 cosine of 40, and that's going to be my x component. That, if I look at this green arrow, is in the east direction, and so that is going to be a positive 25 cos 40. So then if I look at this red line here, this is the y component. Now that's going to be opposite of my 40 degree angle. So for this one, I can just take sine of 40 is equal then to that y component over, again, the hypotenuse of 25. I move the 25 over, and I have 25 sine of 40. Now this one here is heading downwards or to the south, and I have north as my positive direction, so I do need a negative sign there. Now we can do this each time, but if you know it's just going to be the hypotenuse times the cosine or sine of the angle, you can jump straight to these values over here without doing this each time. But this is where that does come from. Now one thing I might recommend is if you always find your angle relative to the x-axis, then all of your x's are always going to be cosine, all of your y's are always going to be sine. If you draw your angle though relative to the y-axis, those two flip. So we could also relate this angle here to a 50 degrees basically east of south, and that would be an equivalent triangle there. But now what we'd have is we'd have sine 50 for the x component and cosine 50 for the y component. And so you can always flip those if you take the angle to the other axes. However, what I would recommend doing, and what I'll do for these ones here, is I'll always reference to that x-axis, and if you reference to the x-axis, x is cos and y is sine, and it just kind of keeps that a little bit more constant. For my last one then, I have 100 meters north, 60 west, and so we can draw that one in then for my last vector. So we're starting on the north axis and we're going 60 degrees to the west axis, so that's heading out like this. Now my 60 degree angle is this one here, so again north 60 to the west. Now that's reference to the y-axis, so I could draw my triangle in here and then reference to 60, but that's going to make then the sine in the x and the cosine in the y. So what I'm going to do instead is I'm just going to reference it to the x-axis, and that's going to be then 30. And that's just always going to be 90 minus the other angle, so it's a fairly easy one to calculate. So now I have the x along the x-axis there, and then the y along the y-plane there, or the vertical plane there. So then I can jump straight to my sine and cosine. So the green line here is heading out this way, that's going to be the adjacent side. So then I can take the net, which is 100, and then just multiply by cosine of 30. Again, we can go through this as well. The cosine of 30 is x over the hypotenuse, and the hypotenuse here is going to be that 100 meters. Again, I could also do 100 sine of 60. That would give me the same answer. Now, if I look at the direction here, that's heading towards the west, so I do need to put in a negative sign there. And then we can go over to the y component. The y component then is going to be the hypotenuse, which is 100, times now the sine of the angle. And so that'll be 100 sine of 30. Again, we could also go 100 cosine of 60, and we get the same thing. Now this one is heading upwards, and so this one's going to be a positive value because it's in that northern direction, which I've taken to be my positive value. Those are my four vectors then, and I split them all up into the x's and y components. So all I need to do now is just add those up together. So 0 minus 70 plus 25 times cos 40 minus 100 cos 30. And if I add those all up together, I'll get negative 137.45, and then a few more after that, and that'll be, of course, in meters. If I do the same thing for my y component, positive 120 minus 25 sine 40 plus 100 sine 30, I'm going to end up with positive 153.93, and again, some more numbers after that, meters. Once we have the net in x and y, now I have a right angle problem, or right angle triangle problem, because this is just the net along the x component, this is the net along the y component. I can combine those two values and then just put them together in a right angle triangle, solve for the hypotenuse and then the angle. So what we have to recognize too is I do still have these positive and negative signs. Now when I put them into the triangle, I want all positive sides because you only have positive sides in the triangle, but the negatives and positives here are going to tell me how I'm going to draw that. So I'm going to just take a starting point. Now if I start with x first, you can do these in either order, the x or the y, but make sure you watch out for directions. This is a negative 137. Now I've taken east as my positive direction, so that means this negative 137 is in this direction. And so that's the 137. Now when I'm writing those out, I am going to put them in as positive values because I'm going to treat them as side lengths to a triangle, which are always positive. This negative sign though tells me I'm going in this direction, so west rather than east. Then when I look at my net in y, that's going to be a positive, so that's in the northern direction. So then this vector here, for the other side of the triangle, this 153, that's going to be towards the north, and I know that because this is a positive there. And so you'll get the direction that you need to put them in from the signs then of your net. So then I can take this one over here, this will be my net displacement vector, and then that's just going to be the hypotenuse of the triangle. So for my d net, that's just going to be from Pythagoras' theorem. If I square that side, I'll get then the 153.93 meters squared, and then plus the 137.45 meters squared. And again, we will take the whole number from our calculator. So we'll add those two together and then take the square root. And again, don't forget this is squared, so we need to take that square root. And so we'll end up then with 206 meters when we calculate that all through. And that'll be then the net displacement along this line here. Now remember that net is from where these ones started to where that one finished, and we always measure the angle at the base of there. So we're looking for displacement, so we have the distance, but we also need then the angle. Typically we'll use tan for those, but again, because we have d net, we could use any one of those trig functions. So we'll take tan theta here, and that'll be equal to the opposite of 153.93. That's the opposite side, over the adjacent side of 137.45. We take the inverse tan of this fraction there, moving that to the other side, and that will then give us a 48 degree angle. Now don't forget to reference this to to one of the axes, and so we're going from the west towards the north. And so my final displacement, if we use then the shorthand method for the cardinal references, is going to be 206 meters. Then we start on the west axis, and then we're going to be going 48.2 because we have three significant digits, degrees then towards the north. So west 48.2 degrees north. Now you could also go just 48.2 degrees north of west, or we could set this up as a bearing or something else as well. So the other method that we can use in order to solve non-right angle triangles is using something called the sine and the cosine law. Now this of course only works if we have a three-sided figure, so 3 vectors in total. But in that case, if we can make that triangle, we can use something called the sine and cosine law to solve for any of those. So this applies both to right angle triangles and non-right angle triangles. However, for the right angle triangles, Pythagoras' theorem is just a little bit quicker, so we do tend to use that. But if you know you don't have a right angle triangle, or if you're not sure, then sine and cosine law is the way you want to go with those. So what we're going to start with for these is we're just going to look at a generalized triangle, and so there's no kind of preference for any one side or the other here. We just have basically 3 sets of labels, A, B, and C. Now those do have to be in angle and then opposite side combinations, but outside of that, it won't matter which one you call A, which one you call B, which one you call C. So if I call this one angle C, and we tend to use uppercase letters for the angles, lowercase letters for the sides, then the opposite side to that has to be side C. And then if I call this one angle B, that's the, again, uppercase B, then the opposite side, so opposite on the triangle, that's going to be my side length B. And then for my angle A over here, of course, the opposite angle A there. And so you can label whichever set you want, A, B, and C. It doesn't really matter, there's no preferred sides, but you just make sure that you're consistent then all the way through. And then when you're looking at your cosine law, that's going to be this one. This is on your formula sheet. A squared equals B squared plus C squared minus 2BC cos A. So A is always the one you're going to be looking for here. So I would probably just even label that your side A. And then the angle that you're dealing with has to be then the corresponding angle to that. So those two have to be set there. The B and the C, though, those can be put in either order. So B squared plus C squared or C squared plus B squared wouldn't matter. And then same thing, 2 times BC or 2 times CB wouldn't matter. So your sides B and C don't matter, but your side length that you're solving for also has to be then related then to the angle then that you're putting into the equation there. You'll notice too that if you have a 90-degree angle, this cosine of 90 then just goes to 0, and then you're left with Pythagoras' theorem there. And so Pythagoras' theorem is basically just a special case of the cosine law. Now, in general, we can use the cosine law whenever we have two sides and an angle between them. We can also use it when we have three known sides, but that's not a case that's going to show up in physics very often. Generally speaking, how we'll use this is if we have two side lengths and an angle, then we can use this to find the missing side length. And that's how we'll use the cosine law in physics. The sine law then uses the same generalized triangle, but again, is typically more typically used to solve for angles. So if I take one of the side lengths and divide it by then the sine of its corresponding angle, that combination should be equal for any side. And so it's typically going to be written out with all three, but we'd never use more than two at once. You can't have two equal signs in the same equation. What this means is I could compare A to sine A to B to sine B, or A to sine A to C to sine C, or B to sine B over C to sine C. So I could use kind of any two of those to make those equal to each other. The other thing to keep in mind, and this is important if you're solving for angles, you can just take the reciprocal of all of these and you still have then the sine law there. And so either one of those you can use. If you're solving for side lengths, this one's easier because the side length is in the numerator. If you're solving for angles, this one's better because the angle's in the numerator. And more often than not, we're using this one to solve for angles, so we will use this one a little bit more often. For the sine law, what you're looking for is a corresponding side angle known. So if I know, say, C and side C, and then one other piece of information, I can use the sine law. So two sides and an angle gives you cosine law, and then the side angle combination, that's going to be sine law. Generally speaking, though, for our problems, cosine law will solve for missing side length, and sine law will solve for a missing angle. So for this first example, we have a ship moving from Liberty Island in New York to Battery, and from there to the Atlantic Basin. So it's just going to be traveling along two different paths, and then we're going to be looking for a net resultant vector. So that's where our three sides to our triangle are going to be coming in. So we're going to draw a vector triangle the same way as we did with our 90-degree cases. We just have then a slightly different looking triangle from there. So when we're doing these, we always want to draw just a coordinate axis, and then we'll draw our vectors in. And so for my first one, and you can draw them in any order, but we'll start with just them, or we'll put them in just as listed. We have this one at 2890 at 65 degrees east of north, and so I'll have one heading out in sort of this direction overall. That'll be 2890 for the length. And then the top angle here, it's east of north, so that's this angle here. That's going to be then the 65 degrees. When we get to the top there, we'll put then another coordinate axis, and then we'll do the next one. So 1830, and that's going to be then due south. So this will be a shorter line, but coming down something like this, we'll have 1830. Now we're not drawing these to scale. You certainly could, but I'm just going to be doing a rough sketch for these. Now those are the two that I'm adding together. My resultant vector, remember, is where I started to where I finished. And so my resultant vector starts where I started with that first vector, and ends at that end of the 1830 due south. And so this then is going to be the displacement that I'm actually looking for. Now to solve this then, I do need to actually put in some angles to make that one happen there. And so if we look at these, I have these two sides. Now I'm going to use cosine to solve for this side length, which means that I need to have this angle. And so if you remember from your cosine, you need the two sides and the angle between them, and so that's why we're looking for this angle. So here we can use those alternate interior angles. So I have this line going up and then this line. So these are alternate interior angles and so this is going to be a 65-degree angle as well. You really do want to draw these coordinate axes in for here. It's just going to make it much easier to kind of place in the angles that you're looking for. So now that I have two side lengths at an angle, I can use then cosine law in order to solve that. So in this case here, this will be the one I'm looking for, d, and then this will be its corresponding angle, and then these would be the other two side lengths and that are going to be interchangeable in that case. So I can take my d squared equals then the other two sides, so I'll get 2890 squared plus 1830 squared minus 2 times the 2890 times the 1830, and then times cosine of 65. And so this just matches up to the cosine law. So this would be, say, that side length a squared, and then I have the two side lengths squared there. So the 2890 and the 1830, those would just be then my b squared plus my c squared. Then I'm subtracting from that 2c and b, and those are just those two again, and then cosine of a, and that has to be then the corresponding angle to the side length I'm looking for. So always watch that the side length you're looking for and the angle then are a corresponding pair, and then the other two side lengths just fill in there. So then my d value is just going to be this solved with the square root, and so I just end up with d equals 2690. And so that's going to be then the distance, this displacement then in meters. And again, don't forget that's d squared, so take the square root when you're coming up with that. So that's going to be the displacement. And now I'm going to solve for the angle. And so the angle I'm looking for here is going to be in this one here. So I'm going to just solve for this corner of the triangle. And if I find that corner of the triangle, then I can relate that to an axis. So I'll use sine law for that. Now that I have this d value, I have a corresponding side and angle. And so I can then take the sine of 65 over top of 2690. That's that corresponding side length. And then I'm going to make that to the corresponding one that I'm interested in. Now I don't need this one down here because that's at the head of the vector. I need this one because that's at the tail of the vector. And so that's why I'm using the 1830. And so I'm going to take sine of that missing angle all over top of that 1830. So to solve that, I multiply the 1830 over. I'll get 1830 sine 65. And that'll all be over top of 2690. And that's going to equal then sine of whatever the angle is that I'm looking for. So I can put those values into my calculator. And what I'm going to end up with then is sine of theta is going to be equal then to 0.6165. And you keep that whole number in your calculator. And then to solve for my angle theta, I can take an inverse sine. And so the inverse sine of 0.6165, and that'll give me then an angle equal then to 38.1 degrees. Okay. So using the cosine law, we can come up with the length of this vector. So then this is going to be 2690 meters there. And then the angle is going to be 38.1. Now the thing with the sine and cosine law is that we don't typically get the final direction directly from the equation because these are typically not referenced to an axis. So this 38.1, this is this angle in the triangle, but that's not referenced to either northeast, south, or west axes. So I have to then always do one extra step to get that angle. So there's a couple ways you can do that, but the easiest way for this one here is north to this top line is 65, and then plus 38.1 more. So I could just add those two angles together, and that would give me then the total angle here from north. And then I could just report that as a bearing. So I could say then that the bearing is going to be equal then to that 65 degrees plus 38.1 degrees, and that then would be 103.1 degrees as a bearing. And so then I can say that the length is 2,690 meters at a bearing of 103.1 degrees. And so do watch for that carefully when you're doing it in this method, because you always end up solving for just the corner of a triangle. That may or may not be referenced to an axis. Typically it's not, and so make sure that your final direction is always referenced to an axis and not just taking the angle that you've solved for. You can also do hanging mass questions with angles that don't sum up to 90 degrees using then the sine and cosine laws there. In this case just the sine law. Our approach is still going to be the same, we just end up with a different triangle. So first of all, I need to know, first of all, what my free body diagram is going to look like. So I do have a tension force heading up in this direction. Now if this top one is 30, then this one here from the horizontal is also 30 degrees. I have a tension force along this T1, and again with those alternate interior angles, this is then going to be a 50-degree angle, and make sure you know which direction the base of that vector is heading out from. And then of course I have my force of gravity, which in this case will just be 40 times g. I can add those up in any direction and then just make a triangle out of those. So if we start just with, let's say T2 here, I'll do my coordinate axis, and this one here is heading out at 30 degrees out in this direction. And so I'll head that one out over here. That's my T2. And this here is then going to be 30 degrees. Now if that's 30 degrees, then this inside one is going to be 60 degrees. I'll draw my next coordinate axes, and then I'll take T1 heading out at 50 degrees in this direction here. And so that'll be my T1, and that's going to be at 50 degrees down in here. Now I'm going to be interested in this, what this angle is. Now if this one is 30, this one is 30, and so what that means then is this whole angle over here is going to be 80 degrees. Now in all the ones we've done previous, this ends up being a 90-degree angle. For these ones then it'll be a non-right angle. Now my third vector, because it's not moving, has to form a closed triangle. So again, do remember that my net is still going to be 0, and so coming straight down should form that closed triangle. This is my force of gravity, and that one of course is just equal to 40 times g. So what I know in my triangle is all of the angles in one of the sides. So this is going to be an 80-degree angle, this is going to be a 60-degree angle. The angles in the triangle still have to add up to 180, so it does mean that this is going to be a 40-degree angle up on the top there. I also, if you'll note, know a side angle combination. So I know this angle over here, and I know this side length over here, and that's a corresponding set, which means that I can use the sine law. And because I know then the angles, I can actually use the sine law then just to solve for T1 and T2. So if we start for T1, the way I'm going to use each time is going to be then just the sine of 80 over f of g. But I'm going to flip that around. I'll put f of g over sine 80 because I'm looking for a side length, and that just keeps my unknown then in the numerator. So for T1 then, I can just take f of g over sine of 80, and that's this combination here, so the side length to the sine of this angle, and that's going to be equal then to T1 to its corresponding angle, which is 60. So it'll be T1 over sine of 60. I can move the sine of 60 over, so f of g is 40g, so 40 times my value of g. Now I'm taking the sine 60 and multiplying it to the other side, so that's times sine of 60, and that's all divided then by sine of 80. And all of that together then is going to equal T1. So if we run that through our calculator, I will end up with a T1 of 345 newtons. Now we can do exactly the same calculation for T2. I just need to reference to a different axis or a different angle, because T2 has a corresponding angle of 40 degrees. But I still have this known combination of 40g and sine 80, so I'll use that again. So again, I have my f of g over top of sine of 80, and that'll equal then T2, but now over sine of 40. And so I can do the same thing as before. I can take 40g times now sine of 40, and I can divide all of that then by the sine of 80, and that should give me then that value of T2. And if you run that through your calculator, you'll get 256 newtons for your value of T2. And so we can solve for non-right angle triangles, or hanging mass questions for non-right angle triangles as well, but we'll have to use the sine law then to do that. Now your homework from this section is going to come from section 4.5, 1 to 8, and then I'll also pull a few from the extension section, so 7 to 9 on pages 151 to 152. Now there are a couple of those in questions 3 to 7 in 4.5 this happens for, where there's something called the ambiguous case. Now the cosine law still works out great, but you're going to have a little bit of trouble finding the angle at this point. Now this is something that we don't want to worry about for Physics 20. We'll spend a fair bit of time in Math 20-1 on this. So the ambiguous case is not something you should worry about for this semester, or for this quarter. But in order for that to happen, you need to use vector components for those questions there. And so just so you have basically some practice using each of those, questions 1, 2, and 6 from 4.5, you should use sine and cosine laws for those. That's going to be kind of the best method for those ones. From the same section, 3 to 5, 7, and 8, use vector components for those. And especially on questions 3 and 7, if you don't use vector components, You may very well get the angle wrong just because of how you've drawn your triangle. And again, that's something called the ambiguous case. If you're interested, I can kind of go through that with you, but otherwise we'll spend a fair bit of time on it in Math 20-1, so I'd like to leave it for them. For the extension ones, use the sine law to solve for those. And if you do that, then that should be the easiest way to approach those. Now, on your tests and your quizzes, nothing will show up with the ambiguous case, so you'll be able to use either the vector components or the sine and cosine law for any non-right triangles. So you don't have to worry about this coming up on tests and quizzes. It shows up on a couple then in the workbook here, so just watch out for that. But if you split it up like this should give you good practice using sine and cosine law and vector components. And then you should be able to do either one then on your tests and your quizzes. It'll be up to you whichever one you prefer to use.